Okay, so I want to start this lecture over worksheets 22 and 23. And I know we left off on question 6 in class. And we're actually going to move on to question 7 here. So in question 7, it says, you can see you have a drawing over to the side here. And I'm going to reproduce that drawing down here. Let's say you got a ring stand. Something like this, and you've got a meter stick going out this direction, and it's being held taut against this string by a mass. And now this is actually kind of a complicated problem in that there is some forces here that maybe we haven't talked about in this class yet, and but it's actually an intro level problem. So I'm going to make it a little easier. I'm going to do the problem the way it's intended to for the worksheet. This is an intro level worksheet, and so I'm going to go ahead and label. Actually, I'm going to hold off on labeling that T. The first question here was something like this. Is, well, what is your point you care about? What is the object? And in this problem, they tell us, problem 7, they tell us that the angle alpha is 24 degrees and the tension is 18 newtons. So what we have here is something like this with this angle right here. This being alpha. And this tension force, let me pick a different color. Let's go orange. All right, so we got a central dot actually being right here at the end of the meter stick. And so I guess you can think of the end of the meter stick as being our object of interest. So we have two forces acting on the end of this meter stick, which, is there more forces on the meter stick? Sure. There is the force of gravity of the meter stick. There is a normal force from the wall or the ring stand, which is acting as like a wall or a horizontal normal force, which is kind of weird. So this problem is actually a little tougher than it looks, but we are going to simplify it. So meaning only two forces here acting on this orange dot. One of them is going to be the force of the string pulling downwards, which I'm just going to call the force gravity. Why is that? Well, let me go ahead and draw it first. So I have this force gravity here from the mass, and then I also have this force of tension here, which I'll make a bright green here. And that's going to be tension right there. So what we want to know here is what is this horizontal component of, say, tension, and what is this vertical component of tension? And we aren't going to worry about, say, the normal force on this string. It's almost like, yeah, it's really, instead of the end of the meter stick being our object, it's more like this string at this point is the object, right? This piece of string where the orange dot is. Because it's almost like we got a normal force pointed from the meter stick this direction, right? That there is some force normal right there. But we're not going to I guess I can leave it there. I'll leave it up there. We're not going to worry too much about that. And it's probably greater than that too. I'm just going to draw it a larger size, because now that I have it there, now I want to do it correctly. So we're saying now that the orange dot, this piece of the string, is the interest area, and then the normal force is coming from the meter stick. The force, so this is like the force of the meter stick on the string. All right, that's kind of what I'm saying. All right, so anyways, all right. I think we're pretty good. Let's see what else. I think they told us that tension is equal to 18 newtons. And so we can go ahead and write that in. So all they want to know here is what is the horizontal and the vertical force to remove this meter stick from this situation, from being held by the string against the string stand. So this meter stick is this object right here in purple. Right, this is your meter stick, and we want to just pick this meter stick up off of the string, and we want to know how much force that's going to take. So really what this is asking is, what is the component of tension that points this way? We'll call it Tx. And the component of that's the horizontal component of tension, and the vertical component of tension, which we will call Ty. And that's really all we want to solve here. Now, they do tell us, I think, the mass, maybe. No, it looks like they don't even give us that. All right, so really, right, all this is just simply asking us to solve for the components Tx and Ty. And we know that this is a 90-degree right angle. So although we can make this problem way tougher, we don't want to overthink this problem because it's not meant to be a lot tougher, right? It's just meant to be pretty much a SOHCAHTOA problem. So here we know that tension right here is the hypotenuse. This is across from 90. Across from alpha, which is this blue angle, which I'll put a little yellow in here too. Let me see if I can get the yellow highlighter. That's normally what we do for our angles. So across from this angle is our opposite, which is Ty. And next to that angle is our adjacent, which is Tx. So what we're going to do then is solve for the adjacent and the opposite. So to get the opposite, we'll start there. Or usually we do the adjacent first. Let's do that. So we'll do the cosine first. I know I wrote theta. I should probably stick with alpha. All right, so we have cosine of 24 degrees is equal to Tx over T, right? And then we can go ahead and plug in what we know. We do know cos 24 will multiply both sides by T. But let's go ahead and plug in something for T. Let's plug in the 18 newtons. All right, so we multiply both sides by 18 newtons. We end up getting Tx is equal to 18 newtons cosine 24 degrees. Plug that into our calculator. Let's see here. I'm seeing about 16.44 newtons. If we check that with the back of the worksheet, this should be the horizontal force required. On the back of this worksheet, so this would be on the back of worksheet 22 is worksheet 21, so we're looking at 7 This is part A, I believe. So 16.4 newtons, and we said 16.44. So that's pretty dang good. So there's part A. So this is 7A right here. This is our answer. That is the horizontal force. Let's go ahead and do the vertical. Let's go ahead and plug in what we know. This is sine 24 equals our opposite, which is going to be ty over our hypotenuse, which is obviously t, but let's go ahead and just plug in the 18 newtons this time. Do that a little earlier. So we can see now that ty is equal to 18 newtons times the sine of 24 degrees. And let's go ahead and multiply that. I'm seeing about 7.32 as ty. So this is the vertical component. Whoops, I don't know what just happened there. Uh-oh. Okay, so this is our answer to number 7B. All right, and I think that should check out. Yeah, so 7B is indeed 7.32 newtons. Okay, so let's go to question 8. So not a huge fan of that last question, but at least we did it and learned something from it maybe a little bit. Mainly just review though. All right, so question 8 says, a child who has a mass of 24 kilograms is sitting on a swing as shown to the right. All right, and then it says you pull the child back with a horizontal force. Actually, one last thing I just want to mention there that we assumed about that problem that I forgot to mention is that for this point, this mystery point down here in the string that had this mass hanging from it, we know if we would have did the free body diagram for the mass that we would have, I'm going to call this T2 for tension 2 because we already had a T, right? So we know that T2 is equal to Fg, that those forces are equal and opposite. So at this point up here, tension is the same throughout the string. So the force that the string pulls with downward here, right, is equal and opposite to the force that tension pulls with upward. So that's a Newton's third law pair right there. And I wanted to point that out. And since from down here, right, we can see that sigma Fy equals MAY, and the object isn't accelerating, so that's 0. And we can see that T2 points up, so it's positive, and Fg points down, so it's negative. We can see T2 is equal to Fg, right? And my point then is up here, as we had, this T2 right here, this is the same as Fg. So if you were, so over here, we just went ahead and drew Fg pointed down as that purple force. So that's how we knew Fg was acting like it was on the string right there. And I wanted to point that out. So here's that, I'll write it in purple up here. Here's the Fg pointed. That's how I knew that was that. Okay, so hopefully that makes sense. I know I kind of, I mentioned something about it, and then I kind of didn't talk about it, so I want to go back and make sure I got that. All right, so anyways, in number 8, a child who has a mass of 24 kilograms sitting on a swing shown to the right, you pull the child back with a horizontal force of F until the angle between the ropes of the swing and The vertical is alpha equals 32. Complete the free body diagram to the right, showing all the forces acting on the child. What is the tension in the ropes of the swing? What is the magnitude of the force that you are applying to hold the child in place? Okay, so let's add another page. Let's start with that. So I think what we have here then is something like, let's see, something like this. Start by just redrawing the situation. Okay, something like that. You know, there's a horizontal, or I'm sorry, a vertical right here, and this is equal, this angle right here is alpha. Let's go ahead and shade that in yellow. All right, and what is the free body diagram for? That's a good question. Is it about the swing, or is it about the child? Or can we just consider the two the same object? It says a child who has a mass of 24 kilograms. Whoops. I don't know what happened there. We're just going to consider it to be about the child and see if we're fine with just that. So we'll go ahead and draw a dot on the child. Forces here. We have tension pulling this direction. And we have force gravity pulling this direction. And they say that there's also, you pull the child back. Okay, so you're giving this kid a push on the swing. So you're going to pull the child back with a force of F. So F is going to point straight backwards. Guess you're not giving them a push, but you're pulling back on the pendulum-like of the swing, and then you're going to let go, and the kid's going to move like a pendulum and move back and forth on the swing. And we see something like this happening. Do we have to worry about a normal force here? And I want to say the answer to that is no. So I guess maybe, and the reason for that might be is that the mass of the swing itself is part of the child. You know, we're considering that the same thing. But yeah, we do not have to worry about the normal force from the swing. So almost like we're considering the child and the swing as one object. Like I said, they're making some assumptions with these problems, and I just want to point those things out so it's not as confusing. All right, so here's what we have. Something like this, 3 forces here in this free body diagram, and that is it. All right, and I'm going to have to pause it right there for a second. Okay, so 3 forces on this free body diagram. Part A is done. Part B, what is the tension in the ropes of the swing? So I think they do tell us alpha. Alpha is 32 degrees. So let's go ahead and pencil that in down here. And we want to know tension. And notice tension pulls, right? And it's all about the person, swing, object. And how are we going to solve for this? Well, tension points in a weird direction. But force of the pull backwards and force gravity point in normal directions, like by normal, I mean our regular directions we work with, like, left, right, up, and down. So let's stick with our normal system, right, where up is positive y, and down is negative y, and right is positive x, say, and left is negative x. So if that is the case, and this is going to be our axis system, then we need to split. Then tension doesn't agree. Tension points up and right. So we got to split tension up. And you might say, well, we want tension. Yeah, I know that. But the thing is, we have to do this to get to the components. And once we have some of the components, whoops, this is a terrible drawing. Once we have some of the components, we can go back and get tension. So this is Tx. And notice this vector I made maybe a little too small. This is T. T is going to be larger than Tx, and T points up and right, so a piece of T should point up. I'm going to call this Ty. All right, so we got T pointing up and right like this. We've got Tx pointing just right like this. Ty pointing up like this. And these are our components. Here's our right angle. I'll draw it in red right here. And so therefore this is SOHCAHTOA, right? And so across from our 90 is our hip. Across from theta is our op. Oh, Tx is our op. That's weird. Adjacent to or next to our angle is Ty, is our adjacent. It's kind of weird where when I drew this 32 and alpha down here, I almost don't like it anymore. I'm going to move it here. And that way it's clear where that angle is. Okay, so which direction do you want to work in here? And it doesn't really matter, I wouldn't say, but let's see if we know a little bit more here. They do tell us the mass of the child is 24 kilograms. All right, so let's make a little note. 24 kilogram child. They don't tell us what the force horizontal is. So because we don't know this in the x direction, don't really want to work in the x direction. See how that goes? I'd rather work in the y direction because I know Fg is mg, and I do know that the mass is 24 kilograms. You might say, well, if you just want t, why can't we just find Tx using SOHCAHTOA, Ty using SOHCAHTOA, and then work backwards and get t? Because a squared plus b squared equals c squared. And you're absolutely right. You could do it that way. That would work too. I'm going to try and stick with this idea of working in one direction at a time, though. So I'm going to pick the y direction first. So I'm going to go ahead and write. So this is going to be y direction. Because I like the idea of free body diagram, pick a direction to work in, right? That's kind of the way I'm trying to get you guys to think about this. So sigma Fy equals MAY. That y is struggling. Oh, it's even worse. All right, so then what are my positive y forces? Well, it's going to be Ty. Negative y force, Fg. Mass is going to be 24. And now the person is just stationary, right? You pull the child back, and there is no up or down acceleration. So Ay is going to be 0. Doesn't always have to be that way, but it is in this situation. Okay, so let's go ahead and do a little math here. We can see 0. Ty minus Fg is equal to 0. Ty then is equal to Fg. We know that Fg is always mg. and Fg is the same as weight, right? So our formula for weight is our mass times 9.81 on planet Earth. That is your weight on Earth. All right, so let's go ahead and plug in the mass, which I thought, yeah, it's 24. All right, it's going to be a little under 240. I'm getting about 235.44 units or newtons. It's a force. Now with that right there, I think we can now work backwards and get T, right? We wanted T. Let me add another page. We wanted T, and I think we can go ahead and do that. Let's go back up and look. So Ty is an is a adjacent. I was thinking a second ago, I guess we can't do it the way I was saying because we don't know T this time, right? We can't just do SOHCAHTOA both sides. We can't do that because we don't know T, so we couldn't do that. I don't think they tell us the tension. All right, no, they don't. So we have to do it this way. So there is no two ways about it. This is the only way to do it. So anyways, we know Ty is 235.44. So let's go ahead and solve for the hypotenuse. We just said Ty is an adjacent. So if I want to know hypotenuse and I have an adjacent, I'm thinking cosine. I think this is alpha. All right, so let's go ahead and plug in what we know here. For alpha, our angle is 32 degrees. And Ty is our adjacent, which we know Ty is 235.44 newtons. Hypotenuse is T, we don't know that. So we're going to multiply both sides by T. Divide both sides by cos 32. Go ahead and crunch this. Make sure your calculator is in degrees when you're doing these. All right, I am getting a larger number, which is right because this is the hypotenuse, which is 277.63 newtons. All right, and I think we're good here. Probably a good check is to check the answers really quick and see if we got it right. 277.63. Looks like for answer 8B, they're telling us it's 277, so just a little bit of rounding there is the difference, so that's all good. Let's go ahead and solve then for part C, which they ask us, what is the magnitude of the force F that you are applying to hold the child in place? So I might go ahead and write 277.63. Let me get rid of this. All right, so there's our tension force. We want to know what F is equal to now, the red force there. And all right, so we're just going to work in the X direction, and we should be pretty good here. So just write that down, X direction. And we're going to go ahead and say sigma Fx is equal to max. And here our positive x force, whoops, is Tx, because it points right in the positive direction. And our negative x force is F. We'll go ahead and set that equal to, let's see here, set it equal to the mass, which is it 24? Yeah. Times the acceleration, which is once again 0 because the swing is just being held in place with the child on it. And so we can say that this is 0. All right, and Tx is equal to F. So if we know Tx, we know the force, we have to pull back with F to hold the child in the swing at that location. All right, so Tx, if we go up and look, Tx is an opposite. So we're thinking we need an expression for Tx, or we need to use some SOHCAHTOA, right? I mean, bottom line. Okay, so since it's an opposite, we're thinking sine theta, should have used alpha, whoops, is equal to op over hip. Alpha is, I think, 32. Opposite is Tx. Hypotenuse is T. We do know what T is now, which is 277.63. So if you want to put that there instead, we can now go ahead and multiply both sides by that, by the 277.63. And what is that equal to? Let me see. Let me get my calculator going here. Sine 32. I'm getting 147.119. So I'm going to say 0.12. All right, so 147.12 newtons. All right, so let's come back up here. Or actually, we can just see it from here. So we'll just sub that in. Whoops, so I draw that again, sub it in right here. And so we're saying then that F is equal to 147.12 newtons. Okay, so pretty straightforward, just using one direction at a time, starting with the Y direction because we knew more. Just going to write that answer in. Should we double check it? Maybe. Yeah, 8C, 147, so we're good. But yeah, starting in the direction we knew more about, which was the Y direction, we couldn't just use SOHCAHTOA and then Pythagorean theorem, like I said, because we didn't know T. We didn't know the hypotenuse, so that wouldn't have worked. So we had to work in the Y direction first to get TY to get T. I guess you could then use TY to get TX using tan theta. I guess you could have did it that way. But whatever. We did it that way, found T next, and then worked in the X direction to find the force pull. All right, and that's it. So let's go ahead and move on to the next worksheet, which is worksheet number 23 right here. Now, these are still first law of motion, it says here. These are similar to the problems we just did, except these are objects in static equilibrium that are just being held in one location. And we want to know about, say for this first one, the forces involved. So here we have a mass maybe between two ring stands, two strings pulling on this point, and it's all going to be about this point. So that we're going to take a look at that one right now. Let's go ahead and add a sheet of paper, and maybe I'll add it. Looks like I already have one, so I think we're good. I always do a redraw just because I don't want to work in that small little area, and I think just doing the redraws is actually helpful sometimes too. So it's almost like we have two ring stands. don't know if these are really ring stands. I'm not sure. I should probably look at this. You got a 3 kilogram mass, so it's probably a little stronger than a couple ring stands. But anyways, I'm going to draw ring stands. So we have something like this. We have, looks like the object is slightly over more to the left. And it says a string is tied between 2 points, as shown to the right. A mass of 3.8 kilograms is hung from the string as shown. As a result, the string makes the angle alpha equals 52 degrees and beta equals 41 degrees. What will the tensions T2 and T3 in the string be? Okay. Where's T1? Well, we can talk about that in a second. I think that would just be the force gravity pulling down, and I think that's why they didn't use T1. Okay, so let's go ahead. Alpha is larger, is 52. Okay, so I think it's kind of, my drawing's probably going to be kind of crummy, but I'll try. All right, I think it's something like this. And this is alpha. And this is 52 degrees. And this angle right here is, what is it, beta? Yeah, beta, and it is 41 degrees. Okay, so it's something like that. And then we have a mass hanging straight down. I'm not sure why I drew that in 3D. Okay, something like that. Okay, and all right, good. All right, let's label T2 and T3. T2 points up and left. So our object, or our, one of the things we're having to spot is the center point, right? And the center point we're interested in is actually going to be this point in the string again. So I think we drew an orange point in the string. I'll do the same thing this time. And this is going to be the point of interest. I think we said T2 points up and left, so I'll go ahead and do that. And T3 points up and right. Now, we have to be careful here with these drawings because you might look at my drawing and say, well, clearly T2 is smaller than T3. And that's not, just because the vectors are smaller, right? The blue line is smaller than the green line, or the blue arrow, the blue vector is smaller. But that's just my interpretation of this. That does not mean that T2, we cannot assume that T2 is less than T3. All right, that's not the way this works, just by the drawing. All right, my drawing is deceptive because it's not that good. So let me just get that out of the way first. All right, so we need one more force here pointed down. In this one, I could call T, but we talked about this last time, right? That T is just going to be Fg of this mass, right? And I think that's why they didn't just go ahead and call it T1. Here's what I mean. If I just come over here and draw this really quick, I'm saying that if you have a mass here and it's hanging from the string and about this point, right, we have something like this. I'm saying that if we look at just the mass, Fg is equal to T1, right? Because T1 pulls up, Fg pulls down on the mass. Now, if we look at this point up here, we can see that T1 is going to pull down on that point. So T1, this is a Newton's third law pair right here. These two green T1s. And this is why I'm just calling T1 equal to Fg. Because if I just look down here at this, right? And I ignore the point I'm interested in the actual problem, and I just look down here at this, it's pretty clear because the mass is just sitting there that T1 has to equal Fg, right? Because sigma Fy equals MAY. We aren't accelerating, so this is 0, and therefore we have T1 pointed up minus Fg pointed down equal to 0, and so therefore T1 has to equal Fg. All right, and that's why I just went ahead, instead of writing T1 there, just writing Fg. All right, that's what's going on. So hopefully that's not too confusing. If you want to call that T1, be my guest. Go right ahead and show this work, and that's fine. But I was just trying to shorten the problem a little bit. All right, so there you go. And of course, Fg is mg. So I think we do know what Fg is going to equal, but I just thought I'd remind you of that. All right, so coming back to the problem, they say got alpha is 52, beta is 41, and a 3.8 kilogram mass. All right, so we're saying that this is 3.8 kg. Okay, so which direction do we start in here? I don't know if it's obvious. X direction we could work with, Y direction we could work with. You might say, I guess the first question is pick a coordinate system, right? Do we use a tilted axis here or not? And the answer is we don't. You might say, well, you got, this force pointed this way, this force pointed this way. The reason we're not going to go tilted here is we have multiple angles, right? Like the 41 and 52 can't agree on a coordinate system. So it's really a bunch of just odd coordinate systems fighting. So what I think is the best solution then is just to go ahead and stick with the normal coordinate system. Split T3 into an upwards force, right, which we'll call T3y, and a rightwards force, which we'll call T3x. I'm not sure where to write this T3y. Dang. I guess I can write it. I don't want to write it there. Son of a gun. Just trying to keep this from getting too cluttered, and I think there's really no way around it. Oops, my eraser's on. Let's put those black lines back there. So I'm thinking maybe I'm just going to write it right here. I know it's kind of rough seeing it right there, but that's where it is. All right, so we got T3y, and then over here on T2, we have a T2y, which is going to point up, of course, and is going to point left. And you might say, why not draw it slightly somewhere else or on the other side, right? If you need more room, draw it on the other side of T2, like over here, right? The reason I don't do that is I like to keep my 41 in the triangle. All right, so that's why. That was a trick we talked about in the last chapter. Okay, so all right, we have something like that, and hopefully that's looking good and making sense. Now, what is the correct direction to start with? I'd probably say the Y direction, and here's why. Fg. You know the downwards Y force, so that's going to open up this problem. What's wrong with the X direction? Why not work there? The reason the X direction isn't as good is that I don't think it's going to get us anywhere, right? I think we're going to get stuck as soon as we start working with it. So let's start with the Y direction first. All right, and if you get it wrong, right, it's not terrible, so. This is the Y direction, so I'm going to say sigma Fy equals MAY. And we are not accelerating, right? That is a common theme in these problems. Mass is 3.8, so we're saying we got 3.8 kilograms, which is, I'm just going to go ahead and write this out. I think force is pointing up. We have T2Y. Let's go back and look at that. We have T2Y. T3y, both pointed up. And then FG pointed down. Okay. So I'm saying, hopefully you can see that. If you can't, go back and pause it and look at that a little longer. So T2y plus T3y, right? Because they're both up, so they're both positive. Minus FG pointed down. Acceleration is 0. So I'm gonna rewrite that as, just so you can see, this is 3.8 kilograms, right? Times 0. So that's why it's just going to be a 0 there. Now, I would like to solve for T2 and T3. So what I'm going to have to do here, I don't want 4 variables. Like if I go back and look at this, this is kind of nasty, right? Because what I have here is I have T2x, T2y, T3y, T3x, FG. I don't want all those variables. It would be really nice if I could just keep T2, T3, and FG, right? That would be ideal. So what I'm saying is, if we could write, if we could somehow yeah, let me show you where this is going before I spoil the problem. Let me show you what I mean, because I think right now if I say it, you'll just be like, yeah, whatever. He did something. You did some math, and I don't get why he did it. All right, so let me keep going here to make it clear why we need to do what I'm saying. Otherwise, this is going to be like, oh yeah, Rodriguez did some crazy math, and I don't know why. All right, there's already enough of that going on. T2y, T3y, and FG. All right, so I'm going to leave T2y like it is. I'm going to leave T3y like it is. And FG, I'm going to call mg. So I'll say minus mg. Let's go ahead and keep going. Mass is, oh dang, 3.8. Terrible memory. Times 9.81. And set it equal to 0. What is 3.8 times 9.81? It's under 40. I'm getting 37.278. All right, and you can see from the looks of this, we're stuck, meaning we can't go any further in this direction. We don't know what T2 or T3 is, so we can't really solve for T2y or T3y, so we're stuck right here. All right, so y direction, kind of, that's as good as it's going to get, right? Let's look at the x direction. I think it's T3x that points right. Yeah, and T2x that points left. That's it, just 2 horizontal forces. Notice I'm using this, right? I'm using, just so it's clear. It should be clear, but maybe it's not. That's my coordinate system, just normal signs. That's where I'm applying them. So T3x is right, so it's positive. T2x is left, so it's negative. Mass is 3.8. Acceleration is 0. So what the predicament is, or what I'm trying to show you, is that in both directions we're stuck. In both directions we have 4 variables. Check this out. T2y and T3y from the y direction. T3x and T2x from the x direction. All right, that's not cool. That's not going to work. So we need to put these opposites and adjacents in terms of the hypotenuse. So so what I'm saying is, if you remember back to SOHCAHTOA, that when we have say when we have a cosine formula, right? You have something like cosine theta equals adjacent over the hip. That the hip, should I say it that way? No, I should say it in terms of the adjacent. That the adjacent is equal to the hip cos the angle. And when we have, so this is a formula right here. And when we have the sine, we see that the op is equal to the hip sine theta. So what I'm trying to say is then we can come down to one of these formulas and start to apply these things. Because if we go back up and look, let's maybe start with the x direction. I think it'll be a little clearer because there's more room to write. In the x direction, that both T2x and T3x are both ops. And so the op is equal to the hip sine theta. Now, T2x is relative to that angle, beta. And T2, let me pick a different color. Let's go gray. T3x is relative to 52. So what I'm saying is both of them are opposites. So they're both equal to the hip sine the angle. But I'm saying that T2x is going to be T2 sine 41 and T3x is going to be T3 sine 52. So T2 sine, so T3x is going to be my positive one. So it's going to be T3 sine 52 minus T2 sine 41. All right. So what I did there, right, is rewrote them in terms of the hypotenuse sine the angle. That is a tricky step. So once again, T3x and T2x were both opposites. And so I wrote them as the hip sine the angle they're relative to. So instead of T3x, right, we have the hip T3 sine alpha 52. And instead of T2x, we have the hip T2 times the sine beta 41. All right. And why are we doing that? Well, let's see what happens when we do it to the other one now as well. Now, looking at the other one, we can see that T3y and T2y, right, which you're interested in now, are both adjacents, right? And I think instead of, looks like we have T2y written first, so we'll get that one. So T2y is going to be equal to, the adjacent is equal to the hip cos the angle. So we're going to have, instead of T2y, we'll have T2 cos beta, or T2 cos 41. So we have T2 cos 41 plus T3 cos 52. All right, let me try that. So T2, we're saying T2 cos 41 plus T3 cos, I think it's 52 degrees, right? Yeah. Okay. So we have something like that there. And then minus 37.278 is equal to 0. Okay. All right. So let's see what we did there. So by rewriting all of these components, all four of them, in terms of their hypotenuse, look what we did. Look how many variables and unknowns we have now, right? It should be obvious. We have T2, T2. We have T3 and T3. And the rule of math is one unknown can be solved for with one equation, and two unknowns can be solved for with two equations. So here you have your y direction equation right here, right, with your two hypotenuses in there, and your x direction equation right there with your two hypotenuses in there. So we have two equations and two unknowns. This is something we can solve for. So how do we do it? Well, we just solve for one of them in terms of the other variable, and then sub it into the other one. So it's pretty straightforward. Let's go ahead and rewrite. This short one's always the nicer one to start with. So let's go ahead and rewrite this as, which one do we want to get first? I don't know. What do we want to solve for first here in the problem? Do they tell us? What were the tensions? They just tell us to solve for both. Okay, so it doesn't matter which order. If I solve in terms, I'll try and solve for T2 first. So let me solve the short equation here for T3. So T3, divide both sides by sine 52, is equal to T2 sine 41 over sine 52. All right, so all I did was divide both sides by sine 52, and I now have this expression right here. All right, and I didn't really care for that. Let me erase that. All right, so what we're then going to do is take this expression for T3 in terms of T2 and sub it right over here. I'm running out of room again. Story of my life in these problems. All right, so we're saying we have, oh boy. Should we maybe simplify that before carrying it over? Yeah, I'm thinking let's make our life a little easier. Let's do that before we carry it over. So let's type this mess, sine 41 divided by sine 52, into our calculator. So sine 41, whoops, that's sine 14, sine 41, enter, it's about 0.656, and we're going to divide that by sine 52. And after that division, looks like we get about 0.833. So I'm going to say T3 is equal to 0.833 times T2. So this is much easier to sub in. So, because otherwise I feel like I'm going to lose some of you here with all the, I don't know, which is just yeah, all the sines and cosines floating around. So let me add another page here below. Or do I have room here? I think I have. I think I'm going to add another page just to be safe. Okay. So what we're going to do here then is we're going to bring this down, right? So I'm going to have T2 times the cosine of 41. I'm just rewriting what's above here. And instead of T3, I'm going to write 0.833 times T2. and that's going to be multiplied by the cosine of 52, and then minus 37.278, and that's newtons, is equal to 0. Oh, that's running out of room there. Let me see if I can, maybe if I get rid of that. Yeah, that's a little bit better. Okay, so we have something like that. Let's try and get this be a little nicer here, right? Okay. Probably the first thing, cosine 41 is a decimal, so I'm gonna go ahead and plug it in. It's not perfect when I plug it in my calculator. It's better to leave it as cos 41 as long as you can. But if I plug it in my calculator and make it slightly not perfect, 0.755 is cos 41. So we have times T2. So that's what we have right there for T2 cos 41. Plus, what is 0.833 times cos 52? That's going to be 0.513. So 0.513 times T2. Notice the only variable we have now is T2. That was the whole point of what we did. Right, we were simplifying, we're substituting to get just one variable. All right, so this is interesting. All right, let's combine the T2s. So 0.755 plus 0.513 is equal to 1.268 times T2. And we'll kick the negative 37.278 over to the other side. So we'll make it positive. And then we can divide both sides. Now it's just easy here, hopefully. Divide both sides by 1.268. Hard to write. All right, so we'll go ahead and do that. So what is 37.278 divided by 1.268? Because that is T2, right? These are going to cancel. I'm getting 29.399, so about 29.4. All right, and then to finish it up, we just plug this back in the first equation. What was the first equation? Well, the first equation was that orange block right there. T3 equals T2 sine 41 over sine 52, but we simplified it into this. So let's just use that. T3 equals 0.833 T2. Okay. Sub in just right from here, right? You guys see what I'm saying? This is going to go right there. That's it. Real simple. We end up getting 24.49, which I could just round to 24.5 newtons. So I'm going to go ahead and do that. All right, and we'll just check those answers really quick. So let's see here. Where's our sheet at, though? It's right here. It's on the back of 23. You can check that. So it looks like you can see right here, number 9, we have 29.4 newtons for T2, which we had, and 24.5 newtons for T3, which we also had as well. So there we have it right there.